I'm speaking to you from the mezzanine gallery of the Buell Planetarium, where they have many interesting exhibits, and among them is this tic-tac-toe machine. They say that you can't beat it. This is the way it works. If I push a button to put an X, the machine immediately puts a 0 in a strategic spot. If I then follow by putting an X, you notice that the machine put a 0 here. Well, since the object of the game is to get 3 in a row, and there are 2 zeros there, I try to block the machine by putting an X here, and then I try to use my own strategy by putting an X there. The machine has beat me. They say you can tie the machine, but you can't beat it. Well, we'll see. See, it can beat you in a hurry. Well, I'd like for you to meet Karl Wawrzyniak, who is a physicist here. And Karl, what's so educational about a machine you can't beat?
Well, it's an excellent opportunity, Ray, to find out just exactly how a relay can work and how it can be made to beat you. This machine you see, Ray, is operated by relays, and they're really telephone-type relays, which the engineering people in the Bell Telephone Company have devised a method of adapting to make a brain or an electronic device of circuits by which your moves can be prejudged with the machine, and the machine will either beat you or tie you. In line with that, if I might, let's see if we can understand something about what it is that operates this machine. If we look to where I'm pointing now, we see a large mock-up model of a relay. Now, a relay is really an electronic switch. It is composed of 2 basic parts. Part A is a coil which is mounted inside the unit, which carries an electric current by impulse with a switch. In your case, the impulse was gotten by your finger pressing the desired button. Mm-hmm. When you pressed the button, the current went through the coil and activated the relay so that the units inside were moved to a contact position and turned on.
That's just like a switch like on the wall that you flip, except this one works with electricity.
Precisely, and unlike the switch on the wall where you can only close one contact, here you can see 2 movable contacts. And in many instances, this is the entire operation below. There are as many as 6 and 8 contacts thrown each time a button is pressed.
In other words, the thing's rigged. Whenever one of those closes, it automatically closes another.
Yes, all of the prearranged possibilities for the tic-tac-toe game have been figured out. For instance, you made a move, and through all of the wealth of experience about the game of tic-tac-toe, the study was made as to where best should the machine move so that you would be beaten or tied, and subsequently the necessary number of contacts were programmed to respond to that particular relay that closed.
How many relays are in there?
There are actually 48 relays on the board. Now, actually, you did not have 48 switches, but in many cases it's necessary for 4 or 5 or 6 of these relays to go into operation when you make a particular move in your strategy.
In other words, on that board back there, any one of those that I push automatically turns on the strategic one to beat me, doesn't it?
Indeed. Let me clear the board, for instance, from the game that you've been playing here to give you an illustration of this. A very popular move, for instance, in tic-tac-toe is to always select a move in the middle. Well, you notice the machine has immediately selected this particular spot to move against you. It goes to a corner. Now, if I clear this, you may see how the programming occurs. The machine always takes the best possible known move. As a reverse of this, for instance, you might choose the corner with an X. The counter move is identical. The machine recognizes immediately it must block the center to beat you in your particular operation.
Now, you said you used the word program a minute ago. That's just like you program a computer. Is this a small computer?
This can be considered a very small computer indeed, because all of the known information about the game of tic-tac-toe has been put into the operation here, and with each particular move that you make, why, the machine then screens out and makes the best possible move. It's interesting, you see an excellent example of what programming is here, Ray. You notice the machine can make no other move. You can progress here, touch this button 1,000 times, and 1,000 times the exact same result will come out. And there is your illustration of programming. This is the right answer.
If you go over to the other corner, will that middle still come on?
You mean if I select this particular point here? Indeed it will. Yes, indeed. The strategy is that this must be blocked first on the reversal of procedure.
If you want to become a tic-tac-toe expert, just study the moves.
Right. Now, one thing to show you how the programmer fits into this operation, Ray, notice that we might choose any one of the four corners if we press the center button. And the programmer, in this particular case, merely had as information, when the center is pressed, block a corner. And he chose as an optimum this particular corner, and that the work of the programmer in thinking through the machine is very beautifully illustrated as that particular selection.
And so it goes, and the reason that I can't win here is because this thing is so automatic that the machine really doesn't have any choice.
No, you can tie as a consolation, but to win is a problem which you cannot devise out of the machine.
Thank you very much, Carl. That's all the time that we have from here. Let's see now where the magic carpet will take us next.